We'll start going over the homework with question 1. The question 1 gave us point P, negative 1, 4, and point Q, 5, 1. So we're concerned with the vector PQ, and it says express it as a linear combination of I and j. So the first thing we have to do is find the component vector PQ. So P is negative 1, 1, 2, 3, 4, and Q is 1, 2, 3, 4, 5, 1. So our vector would look like this, but for a component vector, we want it to start at the origin. So to get that point there, I would need to go down 4 units and over 1 unit. So I need to take this point and go down 1, 2, 3, 4 units and over 1 unit. So it has the same magnitude and direction, and then that final point would be our component, which is 6, negative 3. To write that in terms of I and j, we would say that it's 6i minus 3j. Yeah.
Isn't that the same thing as changing the change in y or change in x of the 2 points?
Yes. Yeah, we're just, that would be written as a fraction, and this is written as a vector, but it's the same calculations, yes.
I already called it.
Yes.
Yeah.
Number 5 and 7 were the next type of problem. For number 5, we're given an R vectored equation, which is 2 cosine of t I plus 3 sine of t j, and a time at pi halves. Remember, often on the AP test, it won't be written as a vector value equation. It'll just be given to you as a vector. So you can use whichever notation you like better. I tend to like the vector notation better. It's just a little bit less writing. And that's also usually how you will see it on the AP test. So getting comfortable with that would be good. For A, it asks us to draw the graph. Just do this on the calculator as a parametric. So that's the easiest way to get a graph of a vector value function, is to treat it as a parametric and graph it in parametric mode, with the I part being the x equals equation and the j part being the y equals equation. Then part B wants us to find some things. We want to find the velocity. The velocity vector, if r is position, would be the derivative of each component. So that's negative 2 sine of t and 3 cosine of t. And the acceleration would then be the derivative of velocity. So negative 2 cosine of t, negative 3 sine of t. And then the next part says to find the speed and direction of motion at the given value of t. I told you didn't have to calculate the direction of motion, but speed is a big concern. So speed is absolute value of velocity, but when we're working in vectors, absolute value doesn't mean just make it positive. It means take the magnitude. So that's the square root of, and then we're using our velocity vector. So negative 2 sine of pi halves squared plus 3 cosine of pi halves squared. The sine of pi halves is 1, so that works out to be 4. The cosine of pi halves is 0. So our magnitude is then 2, which means the speed is 2. And then part D deals with the direction as well, so we're not going to worry about that part. The next type of question, we'll look at 9. Gave us then, again, a position equation. And this time we're working on time equals 0. It wants us to find the equation for the line that's tangent and normal to the curve. So to write an equation of a tangent line, yeah?
I forgot what you said about this, but do we want to be in degree mode for all these?
No. If we're working with trig functions and taking derivatives, we need to be in radian mode.
Okay, what was it that we wanted to be in degree for?
If you're given a degrees in a problem, then switch to degree mode. Otherwise, be in radian mode. The derivatives that we've learned for the trig functions are only true in radian mode.
Okay.
So like that the derivative of sine is cosine is only true if you're working in radians. It's different if you're working in degrees and much more ugly.
Okay.
So anytime we're working with trig and derivatives, we definitely want to be in radians.
All right.
We were asked to find tangent and normal. To write an equation of a tangent line, we need a point and a slope. To find slope, I think of this as parametric and take the derivative of the x part, which would be the I part. So that's cosine of t. And the derivative of the j part, which would be like the y part. So that is 2t plus sine of t. And then we want a dy dx. So we take the y derivative and divide by the x derivative. We're going to evaluate this then at t is 0. So I get 0 over 1 or 0. So that's going to be our slope. To write an equation of a tangent, we need a point and a slope. So to find the point, we're going to plug t into the x and y parts of this. So x is going to be the sine of 0, or x will be 0. And y is going to be 0 squared minus cosine of 0, or y is going to be negative 1. If our tangent line has a slope of 0, that means it's a horizontal line. So its equation would just be the y value of negative 1, would give us the horizontal line. Part B wanted the normal line. So if we're working with normal, then our perpendicular slope would be undefined, and that would be the line x equals 0. If the slope didn't work out to be 0, then we would need to do like a y equals mx plus b or a point slope form with the given point and slopes that we found. But when it works out to be 0 and undefined, it's easier to write an equation of a line. All right. The next type of question asked us to do an integral of a vector function.
What number is this?
13. And to take an integral of a vector value function, you just take your integrals of your two components. So what has a derivative of secant tangent?
Secant.
So secant of t and the I. And then what has a derivative of tangent? Oh man, nothing. Okay, so then we need to change this into a sine over cosine. And we're going to need to do a u substitution on this guy.
Calculator.
Cosine.
We're going to let u be cosine. Then du is negative sine of t dt. So dt is du over negative sine of t. So then this is going to turn into sine of t over u times du over negative sine of t. We still have the j there. The signs cancel, so I end up with just 1 over negative u, which is going to integrate as negative ln of absolute value of u. The j just tags along. And then we're going to finish our answer. So the secant of t I minus the ln of the absolute value of u was cosine j. And then since we don't have any numbers to plug in, we do a plus c. I hate it when tangent comes up in an integral. It seems like it should be easy, but it's not. You can memorize it if you feel like it. I don't have it memorized, so I just do the substitution because I'm better at that than memorizing things. But if you'd rather just memorize it, it might be a handy one to have memorized. It does come up more often than we would like it to. One more problem type to look at, and that was our initial value problems, and I'll look at 17 on that one because 17 was the messier one. 17 gave us a second derivative of r as negative 32j. R of 0 is 100i. And the first derivative of r evaluated at 0 is 8i plus 8j. Solve the initial value problem for r means we need to get an r equals equation out of this thing. So we're going to start with the only kind of equation that we have, which is the second derivative of r. So we're going to start by integrating that. That'll get us to just the first derivative. And when I integrate negative 32j, I get negative 32tj plus c. Then, using that last piece of information, the first derivative should be equal to 8i plus 8j when t is equal to 0. So that means that c is 8i plus 8j. So we're going to bring that back to here and simplify this equation a little bit. So we've got the I part, so I'm going to have 8i plus, then for the j part, I'm going to have negative 32t plus 8 for the j part, kind of combining those like terms of the j pieces. And then we were asked to find r, so we need to integrate again to get to our r equation. That's going to give us 8ti plus negative 16t squared plus 8tj plus c. And then I'm going to use that middle piece of information that says that r is equal to 100i when t is 0. So all that stuff turns into one big 0. So c is 100i. So then I'm going to take that and bring it back to here, but combining it with the I part. So our final answer is going to be that as far as I stuff goes, I have 8t plus 100. And then for the j stuff, negative 16t squared plus 8tj.
It's pretty rough.
Questions? All right, for section 10.4, we really just have examples to work with. There's not any notes per se, so we'll just look at a few examples. In this section, we're looking at projectile motion. So we're going to be thinking of vectors and or parametric equations as describing the motion of something. The motion of an object can be broken down into its horizontal motion and its vertical motion, and that's why we tend to think of these as parametric equations or vectored equations. So in example 1, it says a projectile is fired from the origin over horizontal ground with an initial speed of 500 meters per second and a launch angle of 60 degrees. Where will it be 10 seconds later?
It's not factoring gravity.
It is factoring gravity, yes. It's not factoring wind resistance, but it is factoring gravity, yes. So the horizontal motion of this thing will be our x equation. Nothing is acting upon it in the x direction except for its initial motion. So this thing's firing off like this. As it moves in the x direction, the only thing affecting it is how fast it was when it started going. We are not going to figure in wind resistance. So if I have a launch angle of 60 degrees, then the horizontal motion would be defined by a cosine. So x is going to be the hypotenuse, which is going to be 500, our initial speed, cosine of 60 over any amount of time, so times t. So that ends up being 250 t. For our y motion, though, it matters how fast it was going initially, but it's not going to keep going up at that angle forever. It has to start coming down at some point because gravity is involved in this. So the launch velocity and angle would account for 500 sine of 60 times t. But we need to subtract from that the effect that gravity is having upon this thing. Kind of side note for why this is what it is, because I don't like just memorizing equations. Acceleration, in this problem, we're working in meters per second. So acceleration due to gravity is 9.8 meters per second squared. If we integrate that to get to a velocity function, we're going to have 4.9 t squared. So we need to subtract from this a 4.9 t squared.
Acceleration 9.8 t.
No, acceleration is, oh, sorry, no, it's just t, it's not t squared. Thank you.
Then why is it 4.9?
It's not, it's 9.8, thank you.
Okay.
But we're trying to find position, so that's why I was just like jumping a step ahead of myself. Position is 4.9 t squared, which is what we really are talking about in this problem. I had just jumped a step ahead in my work without actually doing it. So because we're trying to describe the position of this thing.
That number works right.
Yeah. So then our y equation, that 500 times the sine of 60, turns out to be 500 square root of 3 over 2 t minus the 4.9 t squared. So if we want to know where this thing is after 10 seconds, we're going to plug 10 into each of those. So according to x, that would give us 2,500. And according to y, that gives us 3,840. So that means after 10 seconds, this thing is 2,500 meters away from where it started horizontally, and it is 3,840 meters above the ground. Okay?
Fantastic.
Yeah, it doesn't say what, but I mean, if we're firing it with initial speed of 500 meters per second, we're not throwing it, right? This is something pretty advanced. So
It could be me throwing a football.
it could be.
Yeah.
It's about approximately correct, I'm sure.
Have you seen his cans, baby?
That was good when we started.
I was like, baby.
In our second example, we are asked to find the maximum height, flight time, and range of a projectile that is fired with the same information, initial velocity of 500 meters per second and a launch angle of 60 degrees. So the things that we were asked to find are then max height, flight time, and range. All right, so for maximum height, height is a y thing. So from the last problem, our y equation was 500 sine 60t minus 4.9 t squared. And this would be our position function. What's going to be true about this thing at its maximum height? It's going to have a velocity of 0. So we can take the derivative of this. And find out where that is equal to 0. Since we're talking about 60 degrees here, this would be a problem that we would want to be in degree mode.
Oh, that's why.
So 500 sine 60. Ooh, then actually I don't know if this is going to give us the right answer because I just took a derivative.
Sine 60 is weird. 500
Let me see if this actually does give us the right answer because it might not since we just took a derivative.
Okay, so the T applies to everything.
It does. Okay.
sine 60.
I guess it gives us the right answer because we weren't taking a sine of t, we were taking a sine of 60. So I didn't actually take a derivative of the sine. I just took a derivative of the t stuff. If we had actually had to take a derivative of sine because that wasn't a constant, then it would have given us the wrong answer. But 500 sine of 60 is really just a constant. So so that's fine. If it was like a sine of t, that would be a problem with taking derivatives. You wouldn't want to do that in degree mode. Okay, so I saw this thing out for t, and I got t was equal to 44.185. But that's not the answer to our question. So our question said, what is the maximum height? This is a time, that's not a height. So what do I need to do? Plug it back into the y equation. So I need to take this back to here and plug it in to find out that at that time, our height is 9,566.327 meters.
That's very accurate.
Yeah, we wouldn't be this accurate to 3 decimal places, but that's an AP thing. Unless they tell you otherwise, just always go to 3. So that's our maximum height. Flight time. What are we going for there?
1 equals 0. When x equals 0 for a second time.
When x equals 0 for the second time. So it's going to equal 0 the first time when it's launched.
Why did we take a derivative of the position to try to find the time there?
Because we were looking for the maximum height, and when it is at its maximum height, it will have a velocity of 0. So we took
That's right,
position
yeah, okay.
derivative to get velocity to set equal to
That's
0.
what we, yeah, okay, there we go.
So one way to solve for the flight time is going to be to think about taking our x equation from the last problem, which was x is equal to 500 cosine of t. No, cosine of 60t. Set that equal to 0, but that's a problem. It's not going to give us a second answer. So what else is going to be true about parabolic motion in general?
Once the y
Takes the same time to get to its maximum height as it does to get back to the ground.
Yes. Parabolic motion is nice and symmetrical. So another way to find this would be to take the y value and set that equal. Oh, sorry, we would have taken the y. I don't know why I was talking about the x value there. We would have taken the y value and set it equal to 0, and that would give us 2 solutions. So you could do that, but it's solving a messy quadratic. So that's one way to go about it, is setting the y value equal to 0, and that'll tell you when it lands. But that's messy quadratic. Since we already know that it took 44 blah 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 seconds for it to get halfway, it must take twice that to get all the way. So flight time, if you already know the other part, becomes just taking this and doubling. And so the flight time of this thing is 88.37. Range, what is that asking for?
You just plug that into the x.
Plug that into the x equation. Range is asking for how far away did it land. So like how far do I have to travel if I need to like pick up whatever this thing is that I just shot. So we'd plug that into our x equation then. 22,092.48 meters. I don't want to walk to pick this up.
No.
Okay.
It's 22 kilometers.
A 22K. You don't want to do that. All right.